we've really started to see very dramatic events in more recent years, and what we could call the most severe heatwave ever recorded across the whole planet occurred in 2022 in March in East Antarctica. The temperature was 38 degrees higher than normal for the time of year.
That's a huge difference.
Yes, some places got up to an astonishing high of minus 10 degrees centigrade.
Okay, so they should have been more like
usually
minus
more like 50 or something like that.
Hello and welcome to the latest episode of Beyond the Ice, the podcast from British Antarctic Survey where we get you up to speed with newsworthy science and engineering from the polar regions. My name's Em Newton and today I want to find out more about extreme weather events. From the record-breaking heatwave in northern India to the intense flooding in Dubai earlier in the year, you may feel that you're seeing more and more coverage of extreme weather and record-breaking events in the media. This isn't just a media trend. It is an established scientific fact that raised average global temperatures have already led to increasingly severe weather extremes. I'm pleased to be joined today by Louise Sime, who is an Earth system modeller, and Tom Bracegirdle, who's an atmospheric climate scientist. Thanks for coming on the podcast.
Thank you.
We're pleased to be here.
So, normal weather can be pretty extreme, but what do we actually mean when we're talking about extreme weather events in the context of a changing climate?
So, in terms of extreme weather events, what we mean is events that are out of the ordinary. So for us, conditions in Antarctica seem very extreme all the time. But if you're in Antarctica, extreme conditions can be something like minus 10 degrees, which can be actually very warm compared to the normal conditions, which could be minus 40 degrees. So for the delicate balance of the systems, the way the ice and the ocean interact, those differences and extremes can actually have quite large impacts.
So it's abnormal weather patterns or things that are significantly away from average weather or average events.
We're talking about all types of phenomena. So temperature, heat waves, or at least what we could call heat waves in Antarctica. And it doesn't rain very much in Antarctica, but there can be very large amounts of precipitation. But the very extreme conditions have a big impact on the ice and the ocean in those regions.
Yeah, so I mean, it's extremes in an extreme climate, I guess. That's sometimes what is confusing about it. I guess I would just add that sometimes when we talk about it as scientists, we talk about how often something comes back. So we're interested in these low frequency occurrences, be it in temperature or snowfall or whatever else, or even in winds as well too.
But then we're talking about this in the context of climate change, and the talking points there are all about 1.5 degrees C or 3 degrees C. So those figures, they're just the average temperatures for the globe.
Yes, so those what seem small changes on a global average can be larger in some places than others. So over land, the changes in terms of the global average are larger. And also in the polar regions, there's something called polar amplification, where the changes can be up to 2 or 3 times those global average changes. So something like 1.5 degrees would be more like 3 degrees in the polar regions. The other thing is that we feel these impacts more when something is very near the limits of what we normally experience. So, a very hot day of, say, 35 degrees in the UK, if that changes to 38 degrees, suddenly the impact of that change can be much more, I guess, significant.
But then those quite small temperature differences connect to these more specific and extreme events.
Well, I mean, in a way, this is the question that motivates us when we're looking at extremes as scientists is what is that connection? We're all aware that global temperature is increasing. In terms of how that connects to extremes, it's actually really quite difficult and it's quite regional. But it's also really important because the extremes are often what creates the impact on people, and whether we have the resilience that we need to deal with changes in extremes is a good question. The reason it's hard to say something very definite is that we know it's not linear. So we know it's not the case that if the temperature, I mean, you could talk about it as the temperature doubles, does not mean that the amount of snowfall in Antarctica will double. We know there's lots of more complicated feedbacks, but one of the most simple one is that as the air temperature goes up, then the amount of water vapor that can be held in the air goes up much faster than the temperature does. So that means that we sometimes talk about it as the Clausius-Clapeyron relationship. This is, if you want one of the technical definitions,
Absolutely.
then this is one of the reasons that a smaller increase in global temperature or in regional temperature around Antarctica can equate to much heavier snowfall events, just because the air can hold much more water vapour. But then beyond that, the feedbacks can get quite complicated in terms of interactions between winds and sea ice and what's going on in the ocean, and then that can again feed back on the weather patterns.
Okay, so can you give me an example of what an extreme event in Antarctica looks like, one that we've actually seen on record?
Yeah, I mean, there are a number of examples. It's quite a long time ago now, 2002, more than 20 years ago, but there was a very extreme summer in the northern tip of the Antarctic Peninsula. And this is part of Antarctica where sometimes the temperature gets above zero and we can actually have melting at the surface in the summer. And there was a large ice shelf about 50 kilometers across. And an ice shelf is an area of floating ice, so it's quite thick ice. It's there all year round. And this thick region of ice in the summer suffered severe melting on the surface because of very warm summer temperatures. And in a very dramatic few days, of the order of a week, melting at the surface caused or contributed to the collapse of this huge area of ice. And it disappeared very quickly. And this was caused by changing winds, which, as they blow over the Antarctic Peninsula, cause a warming effect on one side of the mountainous region. So it was a remarkable event that had a really clear impact.
It was a really dramatic collapse, wasn't it?
I've also heard a number of more recent examples. So I think there was an extreme heat wave in East Antarctica as well.
So in terms of temperature extremes, we've really started to see very dramatic events in more recent years. And what we could call the most severe heat wave ever recorded across the whole planet occurred in 2022 in March in East Antarctica. The temperature was 38 degrees higher than normal for the time of year.
That's a huge difference.
Yes, so some places got up to an astonishing high of minus 10 degrees centigrade.
Okay, so they should have been more like
usually
minus
minus
50
or something like that.
What's the physical phenomena that causes a heat wave of that extremity in Antarctica?
Atmospheric rivers are one of the names that we use for when you kind of get a filament of very high moisture laden air. In this case, it was coming from relatively tropical regions, and it was flowing quite fast and quite directly, I think, into East Antarctica. And the weather patterns kind of got set up so as it sort of got stuck. And then this really warm, really moisture-laden air was flowing into Antarctica. And it looks a little bit like it got sort of trapped there. And then as it caused heavy snowfall, and as the water vapour is condensed into snow, then this also generates actually more heat as well too. So, I mean, most of the warmth kind of came in with initial air, but the trapping of this air and then the snow-related processes helped increase and sustain this. So the whole event lasted at really high temperatures, as Tom said, for a few days. And then it sort of dissipated over the course of a week or so. And then we came back down to normal chilly Antarctic temperatures after that. I mean, it never got above zero. That's worth saying for most of the high Antarctic sites. But this huge temperature anomaly of 38 degrees was really absolutely staggering.
What's interesting about those two examples is that they both are heat-related events that then have these kind of really specific and quite long-lasting, complicated impacts on the physical environment that aren't necessarily just like it was hot for a while and then that ended. So certainly in the last B ice shelf, you've got that change to the ice shelf. But then I heard that with the East Antarctic one, that actually increased the mass of the ice sheet overall.
Well, that single event contributed to quite an astonishing situation in 2022 where there was more snow fell in Antarctica, and that increased the ice more than the ice loss at the coast from ice shelf melt.
And it's one of the reasons that all these extremes can be so complicated to analyse, because in some sense, like, whilst we think of extremes as usually negative, because maybe we're not prepared for them if they occur in Europe, if there's a heat wave, but we're really not completely sure yet for Antarctica. If there's many more what we classify as extreme snowfall events, it might actually result long-term in more water being taken out of the ocean and placed on top of Antarctica as ice, then enters the ocean. But it's quite hard to calculate this. It will not overall result in sea level going down. That's worth saying. Global sea level will continue to go up because of the heating of the water and the loss of ice from other glaciers, including from across Europe and North America, but also from Greenland. But for Antarctica itself, it's actually a bit uncertain because of the nature of these snowfall events. And as Tom said, the fact that at least in 1 year, there was a little bit more mass put on Antarctica than actually entered the ocean from melting around the edges. It makes calculating what the likely sea level contribution to the global ocean from Antarctica is actually quite tricky at the moment. So in some sense, maybe that's a possible good news angle for extremes for Antarctica.
Rare good news. So does this relate in any way to the extremes we've seen in sea ice? Because there's been a wild few years for Antarctic sea ice.
And this is yet another good question, which has got many scientists scratching their heads. So we do know that the event that Tom described in detail there, this East Antarctic heat wave, happened about the same time as quite a large loss of sea ice in 2022. Because the air masses came from more tropical regions, I think it's not totally clear how or if that sea ice loss was related to that. But I think what we probably would be a bit more sure of is that after that, in 2023 and in 2024, the losses of sea ice around Antarctica have been even bigger. We've lost, I think, more than the size of Greenland in 2023 and 2024. It's a really, really vast area of reflective ice is now not there around Antarctica. That both changes how much sunlight is reflected back out to space, but it also changes how much ocean is exposed to the atmosphere. So we're fairly sure that there will be consequences in terms of the weather for Antarctica. So, I mean, what makes it even more complicated is, of course, the sea ice itself responds to drivers from the weather. So wind forces and wind changes influence how it is blown around and how much it grows. But the sea ice, by its removal and exposing all this ocean to the atmosphere, probably makes it more likely that there'll be more moisture in the atmosphere. So it's likely that there'll be consequences in terms of both average snowfall over Antarctica, but also for extremes. I don't know if Tom would want to go further than that, or whether we don't consider that a work in progress.
Well, there's evidence from the past showing that areas where we've had large declines in sea ice do change the weather conditions at some weather stations. And there's a particular location where you can really see that a period of a number of decades where the sea ice retreated, they lost for the very cold winters that they used to have when there was more sea ice. The weather record there shows a sudden jump from a series of very cold winters that are no longer present. So there's a large warming at that weather station, and it's mainly because of losing cold winters.
So certainly at BAS, it seems a lot of scientific energy goes into improving the models that we're using to predict the future of the Earth. But it sounds like these extreme events can add a lot of complexity to that picture, whether or not that is introducing new and sudden changes to physical environment or having these really complicated feedbacks. That seems like a really major challenge. Is that some of the work that you're focusing on, those specific and perhaps unusual additions to these models?
Yes, absolutely. So Louise and I are both working on major projects looking at how the changes in extreme weather both could be happening now. A really key point is that actually we don't really know the present climate that we're living in very well. The record that we have of the past is no longer a good indication of what to expect now because the planet is warming. So we even need climate modelling to understand our present-day climate, let alone future. Another key point is that these extreme weather events don't necessarily change with the average temperature. So if you have a warming of 3 or 4 degrees, the heat waves themselves may increase by more than that or less. So it's very critical in terms of understanding the impacts of climate change, to know not just how the background climate will change, but these low and high extremes as well, the warm and the cold years.
So there's not necessarily direct linear relationship between the amount of warming we're seeing on average and then the scale of extremity that we might see in
That's
extreme
right.
events.
Two of the reasons that's hard to model is that, first of all, extremes by their nature occur rarely. it can be really hard to measure. If it only occurs once every 200 years, your chances of measuring that extreme is low. So it's hard for us to have enough data. And that makes it hard for us to represent it in the model as well. And then as a third thing, to test that, because we may not have observed key physical processes which are happening because they happen rarely, or possibly when we're not there, or in Antarctica, given just how sparsely it's observed and how enormous it is. And like I say, then we don't know what physical processes to write into Earth system models, and then we really don't know if they're right, because so we recently looked at this for actually more on the sea ice side, and we looked at the models, and all of our most recent climate models, which are used to sort of underpin the IPCC science, they showed the sea ice reduction that we had only happening in some models never, in some models once every 2,000 years. So this means that we don't really know if the physics in the models to represent these are wrong, or we don't know if it actually is a 1 in 2,000 year event. It gets quite tough when you're trying to model extremes on multiple levels. But I would say it's really important as well. So,
but also, actually, if we put the investment in, we do have the technology, the model capability to do a good job, but it requires an investment in running these complex atmospheric models. They take a lot of computational resource, but it is possible if we put the effort in. And this is what these major projects that we're working on at BAS. So there's one called Extant, another one called Surfeit. Although it's difficult, it is possible if we put the investment and the effort in.
Definitely second that. I think we already make progress, and just the fact that we do now have more projects like Surfeit and Extant, which are trying to bring the experts together and make sure that the observations that we do have are brought into the same room, if you like, with the modelers, so that we all put our heads together, and with some of these hard extremes problems, we make progress together.
So if I'm a climate skeptic, I might turn to you and say, how do we know that a particular extreme event is down to climate change? Haven't we always had extreme events? So is the question really here about frequency or extremity or both? And how do you know as a scientist?
Do you want to talk about attribution studies?
Yes. So actually, one of the big parts of the Extant project is on what's called weather attribution. So the UK Met Office, for example, is a real leader on this. And after a weather event occurs, they have the technology to be able to determine whether climate change has contributed to that event and how it would have looked without climate change. And we're involving the Met Office in our project to look at that specific technology and that methodology for Antarctica and Antarctic extreme events.
The way it basically works is that if you run the same type of model simulation, but both with and without the human induced impact. So if you ran the same simulation without global warming and with global warming, and you repeat it enough times, then you can build up a probability pattern of how likely it is that event occurred if we had global warming, or if we had sea ice change, or you can basically set the question up as you want to do this. And it's a really powerful way of, the name says it all, to attribute what is actually causing the extremes. It's not infallible, but it's really, it tells us a huge amount about what is the important factors behind changing extremes.
The thing about extreme weather is actually this is the kind of sharp end of climate change in the way that we as humans on the planet will experience it. And so I guess the main kind of recourse for all of us probably is to be working to reduce emissions levels.
Absolutely.
And that kind of average temperature.
And in fact, if anything, what we're discovering is that with these extreme events and the fact that they can change quite rapidly, even with small global mean temperature changes, it emphasizes even more the importance of reducing our emissions. But if we do that, then we can avoid a lot of the worst impacts of these changes in extreme events that are predicted.
Yeah, reduce your emissions.
You heard it here first, or possibly for the 100th time. Thank you so much for coming in today.
It's a pleasure. Thank you.
Thank you.
Next time on Beyond the Ice, we've got a discussion about communicating climate science in the media. It's led by Tom Sheldon, who is from the Science Media Centre, and he'll be joined by 3 fab and very experienced scientists from the British Antarctic Survey. It's a really interesting and thought-provoking discussion, and we're really looking forward to sharing it with you. We hope you enjoyed Beyond the Ice from the British Antarctic Survey. If you'd like to come back for the next episode, do subscribe to the podcast on your preferred podcast app.